Greetings. Today we're going to be covering two sections. They kind of spread out a little bit. One of them is section 9.4, which is called the pigeonhole principle. The pigeonhole principle. And the other one that we're going to be looking at, we're going to be looking at 9.7, which is looking at Pascal's rule and the binomial theorem. And the reason why I'm doing these two together, they're kind of interesting, they're kind of short, and they're a little bit different than the other material in the book. They both have to do with counting, which is one of the primary focuses in this chapter. But then this chapter goes into probability theory. We've talked about it a little bit, and sections 9.8 and 9.9 get into probability a lot more. We'll do that in the next video. But let's start off with this pigeonhole principle. And the idea is very simple. I would love to draw pictures of pigeons here, but I'm not very good at drawing birds. I don't know, so there's a bird. Does that look like a bird? There's a bird, pigeon. There are a whole bunch of these. And over here there are pigeonholes. I don't know if that would make sense in Namibia. It makes sense over here in the state. A pigeonhole would mean there's some box that's in a tree where the bird might nest. So there's another pigeonhole. And this goes on like that. So the assumption we'll make here is that we want to assume that there are more pigeons than there are pigeonholes. So let's assume that there are n of these, and let's assume that there are m of these, and let us assume that n is absolutely greater than m. And we want to assume that these birds are going to fly into these nests, into these holes. So the conclusion is very simple. At least one box will contain at least two birds. Okay, very simple idea. We could state this mathematically a little more precisely. If we have a function f that's mapping a set A to a set B, and both of these are finite sets, and the size of A is equal to n, and the size of B is equal to m, and n is greater than m, then f cannot be 1-to-1. Okay? That is the pigeonhole principle right there. Now, as simple as that is, that can actually be very useful. Your author gives some interesting ideas here. Example 1. There are 13 people in a room. And what's the conclusion? You can say at least two people were born in the same month. Same month. Okay, again, there are 12 months. If you've got 13 people, 13, there is no one-to-one function of 13 into 12. So you have to have at least 2 people were born in the same month. Example 2. You have 10 White Sox and you have 10 Red Sox in a drawer. How many socks do you need to pick? To guarantee a pair. Okay, now remember what we mean by a pair. A pair would mean that we would either have 2 White Sox or we'd have 2 Red Sox. Well, suppose you were to guess 2. Well, obviously it can't be 2, because if I were to just reach in the drawer, I might pick 1 white one and I might pick 1 red one. But the answer would be 3. If I pick 3 socks out of the drawer, I'm guaranteed to get a pair. I don't know what color they're going to be, but at least I know they would match each other. So that's another example right there. A more interesting example that your author gives. Your author says, consider the following set. Okay, I've got the set from 1 to 8. And what I'm going to do is I am going to pick 5 numbers. Okay, and in light of what we've said before, I'll even say without replacement. From this set. And the question here is prove the 2 numbers selected must sum to 9. Okay, well, this is actually very clever. What I'm going to do is I'm going to take these numbers here and I'm going to pair them up in ways that they sum to 9. So I've got 1 and 8. And I've got 2 and 7. And I've got 3 and 6. And I've got 4 and 5. So notice that these are the ways that I sum to 9. And by the pigeonhole principle, if I'm going to pick 5 numbers from this set, we'll break this set up into these 4 subsets like this. If I'm going to pick 5 numbers, 2 of those numbers must come from the same set here. Does everybody see that? Because I've got 5, basically, I have a mapping from 5 into 4. So I've got to pick one of these subsets, okay? And of course, any one of these subsets sums up to 9. Very cute. Okay, so the last thing to say about this, your author talks about the generalized pigeonhole principle. And again, this is much easier to demonstrate than to state mathematically. Your author says, suppose you have 80 people in a room. Okay, the conclusion is at least 4 people have a surname that begins with the same letter. And the question is why? Well, if I come over here and I go 26 into 80, well, that goes in there 3 times, and that's 8 carry the 1 is 7. So there's a remainder of 2. So that means that 26 goes into 80 3 point something. Okay? It's some number between 3 and 4. Okay? But remember, we're speaking in whole numbers now, so that just says that one of these letters there has to be at least has 4 in it. Now you could see why that could be. Suppose you were to go, well, no, that's impossible. Suppose you were to say every one of the letters, there are only 3 people that have a last name that begins with that. Well, if that's true, then you would only have 3 times 26 is equal to 78. Okay? There's still 2 people that you haven't counted for. Okay, so in other words, it is possible that we could evenly split. The 26. We could split 78 people into 26 groups of 3. But if we have 2 more people, then that's saying that at least one of the groups has at least 4 elements in it, and that's what's called the generalized pigeonhole principle. And that's really all there is to say about this. Pretty simple idea. It's a very powerful idea, and we'll probably encounter it again soon. Okay, we want to talk about Pascal's rule, Pascal's theorem, and the binomial theorem. And I think I'm going to try and make this a little bit easier than what's in your book. I want to take you back to your days in high school where you had algebra and you would multiply polynomials. And if I were to come over here and I were to say to you, well, what is a plus b to the first power? Well, that's pretty easy. You would just go, well, that's a plus b. And if I were to say, well, what's a plus b squared? Well, that's a plus b times a plus b. And I'll come over here and first I'll multiply those two. And that's a squared. And then I'll multiply that. And that's plus a times b. And I'll multiply that. And that's b times a, but that's the same thing as a times b. And then finally, I'll multiply that over there, and whoops, mistake. That's plus b squared. So that's equal to a squared. And I'm going to combine this one and that one together, and that's plus 2ab. And that's plus b squared. And so this is the final result, but what I want to do is I want to write it a little bit differently. First of all, I want you to recall that anything raised to the 0th power is just equal to 1. So that if I come over here, I want to write a squared differently. I want to say that a squared is 1 times a squared b to the 0. Okay, remember, anything to the 0th power is just 1, and we're multiplying it times another 1 times a squared. So you can see that this term is the same as that term over there. And then I'm going to come over here and I'm going to say plus 2 a to the first b to the first. And then I'm going to come over here and I'm going to say plus, and I'm going to say 1 times a to the 0 b squared. And that corresponds to this term right over here. So if I were to say what is a plus b squared, this is what it is right over here. 1 times a squared b to the 0 plus 2 times a to the first b to the first plus 1 times a to the 0 b squared. There are a couple of things I want you to notice here. Notice what happens is that in each successive term that I'm adding, the powers of a, they started at 2, and they kept getting smaller by 1 until they got down to 0. And when I look at the powers of b, notice that the powers of b started at 0, and they went up to 2. Now if I come over here and I want to do a plus b to the third, well, I claim that that's equal to a plus b times a plus b squared, and that's equal to a plus b times this quantity right here, 1 a squared b plus 2 a to the first b to the first plus 1 a to the 0 b squared. And let's go ahead and multiply that out. So first what I'm going to do is I'm going to multiply a times all of these terms. And I get that that's equal to 1 a to the third. Oops, this should have a 0 over here. So that's going to be a times that is 1 times a to the third b to the 0. Plus, and over here, I'm going to get 2 a squared b to the first. And when I come over here and multiply that, that's going to be plus 1 a to the first b squared. And now I'm going to multiply the b's times all of these. So I get plus 1 a squared b to the first plus 2 a to the first b squared plus 1 a to the 0 b to the third. So let's come over here and collect these terms. So this is going to equal 1 times a to the third b to the 0. And now what I want to do is I want to collect the terms where I have an a squared b to the first. So I have one there, and it looks like I have one there. So that's going to be plus 3 times a squared b to the first plus, and now what I want to do is I'm going to collect the terms where I have an a to the first b squared. So there's one there, and there's one there, and I add the 2 plus 1. That gives me 3 a to the first b squared plus, and over here I get 1 times a to the 0 b to the third. So now I want you to notice that when we expanded this out, again, notice that I have this exponent here as 3. Notice I ended up with 4 terms that I'm adding. But the other thing that you can notice is notice that the powers of a started at 3, and they kept going down by 1. And notice that the powers of b kept increasing by 1. So I think I'm starting to see a pattern here. For example, suppose I wanted to come over here and I wanted to do a plus b, and let's pick some big number here now. Suppose I'm going to do to the 5th. Well, I'm going to guess that this is going to take the following form. There's going to be some constant over here, and there's going to be an a to the 5th, b to the 0, and then there's going to be some constant over here, and it's going to be a to the 4th, b to the 1st, plus some constant over here, and it's going to be a to the 3rd, b squared, plus some constant over here, 543 a squared, b to the 3rd, plus some other constant here, a to the 1st, b to the 4th, plus finally some a to the 0, and oops, again, my mistake. It's going to be a to the 0, b to the 5th. Okay, that seems to be the pattern that we're seeing here. And the question is how do I figure out these numbers right over here? Okay, well, okay, let's look at something else again. A plus b to the 0 is just equal to 1. Anything raised to the 0 power is 1. And we know that a plus b to the first is equal to a plus b. And we know that a plus b squared is equal to a squared plus ab plus b squared. Oh, and there should be a 2 there. And we know that a plus b to the third, we just figured that out on the last slide, that was equal to a cubed plus 3a squared b plus 3ab squared plus b to the third. Now remember what's going on here. In front of this a, there's a 1. There's a 1 in front of that b. In this a squared, there's a 1 in front of it. There's a 1 in front of that b squared. And what I want to do here is I want to look at a pattern here. If I come over here, well, there's only one term here, and it's a 1. If I come over here, there were 2 terms, and they're both 1s. And if I come over here and look at the terms, there's a 1 here, there's a 2 there, and there's a 1 there. And if I come over here and I look at these terms, it's a 1, 3, 3, 1. Well, I'm starting to see a pattern here. The first pattern I'm starting to see is it looks like whenever I go down these diagonals here, there are going to be 1s. And that's in fact true. I'm going to put a 1 over there. I'm going to put a 1 over there. And the other pattern that I start noting when I look inside of here, for example, when I look at this number 3, I go, well, gee, that's just 1 plus 2. This 3 over here is 1 plus 2. This 2 over here is just 1 plus 1. So if I want to come over here and I want to figure out what is a plus b to the fourth, well, 3 plus 1 is a 4. 3 plus 3 is a 6. 3 plus 1 is a 4. If I want to figure out a plus b to the fifth, I get a 1 there and a 1 there. This is 5. This is 10. This over here is 10. And this is 5. So in fact, what I've just done right over here is I have figured out the numbers to put in here. It would be 1, and then a 5, and then a 10, and then a 10, and then a 5, and then a 1. Neat. But let's notice something else here. Let me redraw the triangle. And yes, this is called Pascal's triangle. And it goes on forever and ever and ever. And it keeps going down there like that. For example, let's come over here and just look at this row right over here. And what I want you to note is that those entries really correspond to 2 choose 0, 2 choose 1, and 2 choose 2. Okay, remember that n choose k, this is equal to n factorial over k factorial times n minus k factorial. Okay, so for example, if I have 2 choose 0, that's equal to 2 factorial over 0 factorial times 2 factorial. Remember, 0 factorial is 1, so this is just equal to 1. Okay, if you come over here and you look at this row over here, that's really 3 choose 0, 3 choose 1, 3 choose 2, and 3 choose 3. If we come over here and look at this row over here, this is 1 choose 0, and this is 1 choose 1. So we can see actually what we've done over here is we have a new way of writing Pascal's triangle. We can either write it with these constants in here, or we can write it in terms of these n choose k symbols over here. Remember, these were our symbols for doing combinations, okay? And we get a very, very interesting thing over here. For instance, over here, remember I said that that is equal to that plus that. Well, so if this is 4 choose 0, 4 choose 1, 4 choose 2, we're saying that 4 choose 2 is actually equal to, that's 3 choose 0, that's 3 choose 1, plus 3 choose 2. And in fact, we have a very interesting theorem here. We can say that n choose k is equal to 1 if, well, we can see it's equal to 1, these things going down here. It's equal to 1 if n is equal to k or k equals 0. If n is equal to k, we're grabbing all these ones over here. If k is equal to 0, we're coming down over here. But in the other situations here, we have that n choose k is equal to n minus 1 choose k minus 1 plus n minus 1 choose k. Everybody see that? This is just this is the generalization of this number right over here. Okay? So in fact, here's another way to think about this. Is referred to as the binomial theorem. A plus b to the n is equal to the summation from k equals 0 to n of n choose k a to the n minus k b to the k. Now that looks really scary. Let's just do an example of this again. Let's consider a plus b to the third. Well, that's equal to the summation from k equals 0 to 3 of 3 choose k times a to the 3 minus k times b to the k. Well, let's go in there and stick some numbers in there. When k is 0, oh, this shouldn't be, we have a mistake. That should be a k. Okay, so in this case over here, when k is 0, I'm going to get 3 choose 0 times a to the 3 minus 0 times b to the 0 plus 3 choose 1 times a to the 3 minus 1 b to the first plus 3 choose 2 times a to the 3 minus 2 and b squared plus 3 choose 3 times a to the 3 minus 3 b to the third. Well, let's figure these things out. 3 choose 0 is just equal to 3 factorial over 0 factorial times 3 factorial, Well, that's equal to 1. Okay, 3 choose 1 is 3 factorial over 1 factorial times 2 factorial. Well, that's just equal to 3. 3 choose 2. That's equal to 3 factorial over 2 factorial times 1 factorial. That's equal to 3. 3 choose 3. That's equal to 3 factorial over 3 factorial times 0 factorial. That's just equal to 1. So this is 1 times a to the 3 minus 0 is a to the third plus b times b to the 0 plus this term over here now, that's going to be 3 times a squared b to the first. This term over here is going to be plus 3 times a b squared. And this term over here is going to be plus 3 times a to the 0 b to the third. And again, we just recognize that as being a to the third plus 3a squared b plus 3a b squared plus b to the third. So that works out. What you might want to try for practice, it'll take you a little bit longer, is calculate a plus b to the fifth using this formula over here. So that would equal the summation from k goes from 0 to 5 of 5 choose k times a to the 5 minus k b to the k. That would be a good practice exercise for you all to try.